Hello everyone. CNC electronics are not easy. A customer sent me the electronics from his CNC machine to be put into a cabinet and rewired. The components that the customer brought in are a transformer that converts 220 volts to 4 pairs of 70 volts each, a 24 volt power supply, which provides the power for the proximity switches, a VFD, 3 drivers, and 1 extra because he thought that one of the drivers was bad for the x-axis because he stated that the x-axis would immediately turn off when he turned the system on. A contactor that allows the system to be controlled by a push button, and a 200 kHz Mach 3 USB controller, which has 16 inputs, 8 outputs, a PWM signal for the speed for the spindle, a way to sense the spindle speed using S plus and S minus, which he doesn't use, and the axis outputs. This is X, step and direction, Y, step and direction, and Z, step and direction. There are 2 terminals for A, step and direction, but this board doesn't have the 2 optocouplers for the 4th axis. So this is considered a 3-axis controller. While putting the system together, I tested the system in a systematic way. I would power up the contactor, measure the output, making sure the output measured the same as the input, then connected the transformer to the output of the contactor, then measured the pairs output from the transformer. I then connected the transformer output to each of the drivers. The output is 70 volts AC, and these drivers are able to accept 18 to 80 volts AC or 36 volts to 100 volts DC. I tested all of the drivers to see if they are working, and I noticed that all 3 drivers had the green light and they were powering up successfully. And at this point, I was hoping that the X driver was just having a loose connection or something to the power supply, and that's why the X driver didn't work, or it's something else. From the testing, all the components are working so far, so I went ahead and started to install the remaining components and test them. Starting with the low-hanging fruit, like connecting the VFD to the output of the contactor and confirming that works, and connecting the 24 volt power supply to the contactor and confirming that that one works as well. In this project, to save money, the customer decided not to have cables made since he was going to be using his own cables, which is understandable because taking cables out of a machine and out of all of the cable carriers could be quite a task. And if the cable is good, there's no need to replace it. And his cable has shielding, so it would be easy for him to just connect the shielding to the body of the cabinet and he's ready to go. And these connectors I'm using have screw terminals to make it really easy to connect cable. The on-off button for this system is a simple push button that has an LED indicator. This push button requires 24 volts to light up the LED indicator, and this is the benefit of using a contactor. Contactors operate by engaging a coil that will allow these terminals to pass through to these terminals. The coil is generally labeled as A1 and A2. This contactor had to be replaced with a new contactor because his contactor was rated at 50 Hertz and not 60 Hertz, which is the frequency that we have in the US. When this contactor was engaged, it provided a humming sound, and it was rather loud actually, so I didn't want that to be a problem that the customer experienced. Because the contactor is engaged using the 220 volts, but since the coil winding is 1K ohm resistance, it is only drawing 0.2 amps, so the push button doesn't need a high current amp rating to operate a contactor. So this takes me to the part of the process that I need to diagnose the problem. Why isn't the x-axis working? So I went ahead and connected all the lines to the controller, the signals for the step and direction to each driver, and test the controller. So let's go ahead and do that. I'd like to take a moment and ask, if you're enjoying this video, please press the thumbs up button. And if you enjoy these kinds of videos like CNC Electronics or bare metal microcontroller programming, consider subscribing. I have a lot of really cool content coming up in the CNC Electronics and in the microcontroller side of things. In the description, I have links to a lot of the tools that I use, and consider going to buildercnc.com for CNC related products and tutorials. And also go to newbiehack.com for the bare metal microcontroller tutorials and kits related to that. I'm just going to spin the z-axis, the y-axis, and the x-axis. I'll start with the x-axis, and I get no response. I know that when I press the left and right arrow keys, the x-axis digital readout is changing, and that the LED on the controller is blinking, informing that you have communication between the computer and the controller. Now let's try the y-axis. The y-axis is turning, so I know that the controller is connected to the drivers correctly, and the Y driver works. Now let's try the z-axis. So the z-axis works, so I know that the z-axis is connected to the controller correctly and the z-axis driver works. So in this case, how do I know if the problem is the motor, the x-axis driver, the connection between the motor and the driver, the connection between the driver and the power supply, the connection between the controller and the driver, or if the controller is bad? There is a way you can diagnose this problem without using any special tools, just by using the equipment that you have in the CNC Electronics. We're going to use the good drivers and the good motors to diagnose the problem in the x-axis. First of all, we can see that the x-axis has a green light, so we can somewhat safely assume that it's getting the right power. But we should measure the voltage coming from the power supply to the driver to confirm. But we really don't even need to do that, because I'm going to show you a way we can swap connections to determine the problem. We know that the y-axis motor and connection and the signals are good. So we can use this as a resource to figure out what is going on with the x-axis. So let's go ahead and do a couple things. I'm going to turn off the machine first. Anytime you want to make changes to the connections with the electronics, you want to make sure that the power is turned off and that all of the power has dissipated from the system. You can see that the LED is still lit up and it just fades away. That is showing you the power going out of the system, but I would still wait about 20 seconds after that just to confirm that all of the power is out of the system. If you disconnect motors or disconnect connections from the drivers while the power is on, or there is still power in the system, you can burn the connections at the driver and also destroy the driver. So since we know that we have a good connection between the y-axis motor and the driver, and we know that the y-axis motor works correctly, we can go ahead and take this connector and move it to the x-axis driver. So let's go ahead and do that. Take this one out too, because it's getting in the way. All right. Okay, now that I have the y-axis motor with the proper connections to the motor in the right combination, and I have the connection from the power supply connected to the driver, let's go ahead and try moving the x-axis, because it's still connected to the x-axis signals. So we still have to try using the x-axis left and right jog buttons to see if the driver causes the y-axis motor to move. You also want to make sure that anything hanging is not in anywhere near where it can arc something else. Let me go ahead and try to put this back to see if I can keep this safe. I could plug this into the y-axis. Yeah, I'm going to go ahead and do that, just so it's not hanging around. Another added reason to plug the x-axis motor wires to the y-axis is I can test the y-axis to see if it moves the x-axis motor, which will tell me if the x-axis motor actually does work and that the wires are configured correctly. So I'm going to go ahead and move the x-axis, and we're getting no response, meaning that at this point it looks like maybe the signals are bad or the driver is bad. So let's go ahead and move the y-axis, which we know that the y-axis driver is connected to the x-axis motor. So now we know that the motor is good because we connected the x-axis motor to the y-axis driver. Now we can go to the next step to see if the signals are good or bad. Now we can put the x-axis and y-axis motors back to where they belong, because we know that the x-axis motor is good, it's working. So now we can go to the next step and look at the signals. So now let's swap the signals between the y-axis and x-axis. Actually, I'm not going to put the x-axis down because it doesn't have enough reach. I'm going to go ahead and just plug in the y-axis signals to the x-axis. So now if I move the y-axis, it should move the x-axis motor, since the x-axis motor is connected to the x-axis driver. And this will determine whether the driver is bad or the x-axis signal is bad. So if it does move the motor by connecting the y-axis signals to the x-axis driver, it'll confirm that the driver is still good. Okay, I'm going to start moving the y-axis, and it does move the x-axis. That was a very loud thunderclap that just happened. So now we know that the driver is good. We can conclude that there's something wrong with the controller or the way that the controller is wired to the driver. So it could be that the connection between the driver and the controller, or there is something wrong with the controller. I'm going to go ahead and put the signals back where they belong, and I'm going to use a multimeter to test the connections between these terminals and the terminals on the controller. So this is 5 volts, the red wire, going to the pulse plus, and 5 volts going to the direction plus. The pulse is the same thing as step, or it's also the same thing as CP on some drivers. So I'm going to put one lead on the screw of the terminal, so I know that it's not an issue with the way the wire is screwed into the screw terminal. And I'm going to go ahead and test it against the 5 volts, and I get a good connection. I'm going to do the same thing with the direction plus, even though I know that it's not the direction because we didn't get the motor spinning at all. So it's generally a pulse issue. So now I'm going to connect it to the X step on the controller and the pulse negative on the driver. And I get a good connection between the X step and the pulse minus. So I'm going to connect it to the direction minus and the X direction. And there's a good connection there. So that means that there's probably an issue on the controller itself. These 6 integrated circuits here are optocouplers. And this one is for the X. This was the X step and the X direction. This is for the Y step and Y direction. And this is for the Z step and Z direction. So I'm going to take this controller out and do some testing with the multimeter to try to diagnose where the problem is on the controller itself. According to the schematic, the XS or YS or ZS is connected to this chip, and this chip respectively. So the XS is connected to this chip, directly connected to the pin number 6, which is this one right here. But before it connects to this pin, it is pulled up to 5 volts with a 4.7K resistor. I'm going to go ahead and test the XS to this connection to make sure that it has a connection, and also the YS to this connection just to make sure that that is true. Okay, so the XS first. That's correct. The YS. And that's correct. And the ZS. Okay. So we shouldn't have any connection between the neighboring pins. So let's just make sure of that. The YS. Make sure we have a good connection. Okay. And the XS. Looks like we have connection between all of these pins. And what that tells me is there's a short on the board somewhere. So is it a short between the X and the DC 5 volts, which it does have a pull-up resistor between those two. So let's try that. This is the 5 volts DC. And you hear that it had a little bit of a beep, but it doesn't stay on, which means that there is a diode connection or a resistive connection between the two. Okay, so now let's go ahead and see if this gets connected to ground in some way, because the pin number 5 and the pin number 6, the pin number 5 is connected to ground, and pin number 6 is connected to the VS. So let's try ground. And this is ground here, and this is also ground. So So that means that the XS, the single connection to that chip, is connecting to ground somewhere, or the chip is bad. I'm going to look at this more closely to see if there's any connection between the XS and ground before it gets to this chip. This is the chip that is the culprit here. These are the leads of the chip, and there doesn't appear to be any shorting to ground with regard to the PCB. There's also no resistor here to pull up to 5 volts, so there couldn't be any shorting going on there. This is pin number 5, which is connected to ground, and that's connected to ground through a capacitor, a filtering capacitor, and that's not connecting to pin number 6 either. So I'm going to go ahead and desolder the chip, take the chip out, and see if I still get a short to ground on the XS connection. Okay, the chip has been removed. I'm going to go ahead and see if it's still shorted to ground. I'm going to connect the XS to the pin it's supposed to be connected to. That is good. I'm going to test it with the neighboring pin, which it was shorted to. We can see that it's not shorted anymore. So if I connect the XS to ground like before, I should be getting nothing. So the problem was the optocoupler that was located here. I've informed the customer that he can either wait for me to replace this chip or to add a completely different controller into the system. A new controller would be more of an immediate change because I'd have to wait for this to be delivered. But I just noticed something, that these two chips are also the same optocoupler that's over here. So I might actually look to see what functions these have. So this optocoupler here, which is labeled U8, is connected to the S plus and S minus to receive speed information from the spindle. He doesn't have a need to use the speed input, so I'm going to go ahead and desolder this optocoupler and solder it in the X-axis place. So I have successfully moved this optocoupler from this location, U8, to U1, to its new location. Let's test to make sure that the XS is not being shorted to ground. And that's good. It's just giving me a beep, meaning there's resistance between XS and ground. So let's go ahead and put it to this pin again. That looks good. And that's fine. Looks like it's not connecting to any other pins like it was before. So let's go ahead and try it in the system. All of the connections are put back together for the outputs, the step and direction connections, and the inputs on this side. And all of the drivers are connected to their respective axes and to their motors. I'll try the X-axis first. So good news, that problem is solved. Now I'll try the Y-axis. And finally, I'll try the Z-axis. So they're all spinning, so those tests pass. The last thing that needs to be tested in the system are the 4 inputs for the proximity switches. The customer currently uses proximity switches, and the style of proximity switch is NPN and normally open. They look a little bit different than these, but this has the same connections and requires the same voltage. The way proximity switches work is you put it near metal, and you'll see that it engages when metal comes close to the end of the proximity switch. The connections that I use are white for the output, black for ground, and red for plus 24 volts. And then there's the shield. And I'm just providing pigtails for the customer because the customer has these already wired throughout his system. So I'm providing this to him, and I'm providing this explanation for him. The black wire that comes out of a proximity switch is the output. The blue wire that comes out of the proximity switch is the ground wire, and the brown wire that comes out of proximity switches is for positive voltage. Because the controller works off of 5 volts and the proximity switch requires 24 volts, a resistor needs to be added between the output and the plus 24 volts on each of the connectors. This is the configuration for NPN. If it's a PNP, you would need a resistor in line with the output going to the input terminal. So let's go ahead and test. For the first one, you'll see that the proximity switch indicator will light up when I get metal close to the end. You'll also notice that the LED on the board is toggled. So that's an indicator of the proper functioning of that particular switch. So now I will switch it to the next one. You can see that one works as well. Now we'll switch it to the third one. And that one works. And finally for the last one. And this one works as well. I hope you found this video informative and you got something out of it. Thank you for watching.